In this example, we want to find the resultant force of two vectors in 3 dimensions acting at a single point. So we want to start this with our standard solving procedure. We need to write down what are we asked to find. So we want to find this vector r, and I'll write here because we know there's these two vectors fb and fc. So it's the sum of these two vectors. So notice here I'm using the vector notation. I want vector r, which has a line over it, and fb and fc here I'm adding two vectors in 3D together to get this resultant. And we have some information here in the given that I also want to record. So we're told the magnitudes of these two vectors. So fb is 560 newtons and fc is 700 newtons. And this will come into play when we're adding our vectors together. Notice here that I did not write a line over fb or fc because here I'm talking about magnitudes. So fb without a line is the magnitude of vector fb, which is what I wrote above. So we're given this diagram here. It has some coordinates on it, or it has some measurements in the x and the y and the z directions. So I want to make my own diagram here that I'll be able to use to solve this problem. Right, so my diagram, it's going to look pretty much the same. Now, when I'm making my diagram, when I'm adding my vectors together, I need to center it somewhere. In this case, they kind of tell us what to do because FB and FC are both emanating from A. They're both acting on point A. So what I can do is, A is going to be kind of what I'm really concerned about in my drawing here. Right, so I have this z-axis. I'm going to stick with the axis system that they provided when I'm doing this. So I need to make sure that I explicitly mark what the axes are, or the positive sense of these axes here. So I'm going to again stick with their x, y, and z definitions as I'm doing this. And I have my point A up here. Now, whenever we're in 3D, I think it's really helpful to write the coordinates of what are going to be important points that we're going to be considering. So point A in the x, y, z coordinates, again following what was just given to us, in the x direction, it's 0. In the y direction, it's 0. And in the z direction, so basically what we want to think of is how do we go from the origin to this point? Well, here's the origin. We don't have to go anywhere in the x or the y. We just have to go 6 meters in the z direction. So A is located at 006 meters. All right, what are other points that are going to be important? Well, B and C will also be important, so I'm going to mark those. And now our diagram doesn't have to be to scale. That's why we're putting in very explicitly the locations of these points as numbers, so we're going to be able to use them later. So how do we go from the origin to B? Well, in the x direction, we go a positive 2. In the y direction, we're going along actually the negative y-axis, so negative 3 in the y, and it is in the xy plane, so 0 in the z direction. And C is also going to be important. We'll see why in a second these points are going to matter. But again, with its coordinates here, we have to go in the x direction a positive 3, a positive 2 in the y, and then again, it's also in the xy plane, so 0 in the z direction. All right, so why do B and C matter for this as we're putting together the diagram? Well, going back to what we're trying to find, we are adding vector FB plus vector FC. And in 3D, thinking ahead a little bit, what we're going to need to do is find the Cartesian coordinates of FB and FC, put it in the component form. Then we're going to be able to add our like terms, and then we're going to be able to find our resultant vector. So in the diagram, we're shown that, for example, FB is pointing from A to B. So we know that it acts along this line from A to B. So I can draw that force. I know its direction, points from A to B, and I'm actually told its magnitude was 560, which I could put in the diagram, or I'll leave it off for the moment. So also important is going to be FC, which points from A to C. So on our diagram, I will represent it with this arrow that points from A to C. And I guess in the diagram I will include that I know the magnitude is 700 meters. of FC and 560 for FB. Now, we have a diagram we can use now, so now I can go over and start looking at some equations that we want to be using for this. So I'll call it equations EQS. So the idea we're going to be using in 3 dimensions, it's true for any vector, is that, let's say vector FB, we can write as its magnitude times its direction. So we can say it's FB times U hat B. And FC is also going to be its magnitude, FC, times its direction. I'll call that U hat C. So FB and FC, again, we were given. So if we can find U hat B and U hat C, well, we can multiply the magnitude times the unit vector, the direction, and then we will have the Cartesian component form of these 2 vectors. So again, FB, FC we already know. So let's start by looking at, I'll call it UB. So how do we find any unit vector is going to be a position vector, a normalized position vector. So it's the position vector divided by its magnitude. So I'll be able to find this by if I can find RAB, so the position vector that points from A to B divided by the magnitude of RAB. And this is where writing the coordinates is really going to help us. RAB is the vector that points from A to B. So how do I write that? Since I have the coordinates, it's actually going to be pretty easy. The position vector is always going to be the end point minus the start point. So if we look in the I direction, if we look at point B, it has an I value or an X value of 2, and the start point A has an X value of 0. So 2 minus 0 is going to be 2I, is the I component of RAB. Right, now the J component, B, the end point is at -3, and the start point is 0. So -3 minus 0 is -3. So 2I minus 3J, and then K. So the endpoint B is at 0 in the K direction, A is at +6, so 0 minus +6 will be -6 in the K hat direction. Okay, so that is RAB, endpoint minus start point. Now I need to divide this by its magnitude in order to find the unit vector that points from A to B. And I just call it U hat B. I could have called it U hat AB, as long as it's indicating what this means. This is the unit vector pointing from A to B. All right, so how do I find the magnitude? In 2 dimensions or 3 dimensions, it's the same. It's going to be the square root of the sum of the squares of the components. So in this case, my components are 2, 3, and 6. We're squaring everything, so the sign at this step doesn't matter. So it's going to be 2 squared is 4, plus 3 squared is 9, so that's going to be 13, plus 36 is going to be 49. So it's going to be the square root of 49, which is going to be 7. Right? So again, square root of 2 squared plus 3 squared plus 4 squared, that's the square root of 49. That comes out to 7. Now, in this example, it's nice and convenient because we have nice round numbers to be working with. That won't always be the case. But in this case, we have an integer on the bottom of 7. So I can now write more compactly my U hat B. So I can put this together, and that is going to be 2/7 I minus 3/7 J minus 6/7 K. Now, again, here I'm leaving it in fractional form. I could write a decimal equivalent with two decimal places or 3 decimal places. That will be okay. Usually when I can write it as a nice fraction like this, I will stick with a nice fraction like this. So either is fine to write, but I'll stick with this. All right, now I also need U hat C. So this would be the same idea. I need the vector, the position vector that points from A to C in this case. And then I will divide it by its magnitude. Right, so endpoint now is C. So same idea as the previous one. It's going to be the endpoint minus the start point. So 3 minus 0 is going to be 3I. And 2 minus 0 is going to be plus 2J. And then 0 minus 6 will give me a -6K. And the components of this, 3 squared plus 2 squared plus 6 squared, is actually the same as before, the previous one, so it also will have a magnitude of 7. So this is going to be 3/7 I plus 2/7 j minus 6/7 k. So now I can put together, going up back a little bit, I have u hat b, I have u hat c, the direction vectors that point, the unit vectors that point from a to b and then a to c. So now I can put fb and fc into their Cartesian component form because I know their magnitude, and now I have found their direction. So now in ijk form, I can find fb. So that is going to be 560 times 2/7 I, I'll write it long form for this one, 3/7 j, negative 3/7 j, minus 6/7 k. I have a scalar times a vector, so I am just going to distribute in the 560 into the rest of my vector, and I can just combine everything. So this is going to come out to nice round numbers again, to 160i minus 240j and minus 480k. And this will have units of newtons. I will, just to remind myself what units I'm working with, it's a force, so it's in newtons. So again, the 160 is 560 times 2/7. The negative 240 is 560 times negative 3/7. And the negative 480 comes from negative 6/7 times 560. And then I'll do the same thing for FC. I won't write down all the details here. Its magnitude is 700, and we found its unit vector was 3/7 I, 2/7 j, negative 6/7 k. So multiplying the 700 by each of those components, I'm going to find here that it's 300i plus 200j minus 600k, and then that's also in newtons. All right, so I'm almost there. I have the two vectors I wanted to add together, going back up to the given. I wanted to find the resultant vector, which was FB plus FC. I have FB and FC in component form now, so now finding the resultant is going to be relatively easy. It's just going to be an addition problem. Right, so the resultant vector R, when these two forces are acting simultaneously, once I'm in component form, I'm going to add the like terms. So I'm going to have 160i plus 300i is going to be 460i. Negative 240j plus 200j is a negative 40j. And negative 480k plus negative 600k, I'm left with a negative 1080k. And then this is going to be in newtons. Right, so that is what I was asked to ultimately find in this one, is that resultant vector. And now we're in 3 dimensions. So I'm going to say typically in 3 dimensions, you can leave your resultant vectors and all of your vectors in the component form. We're not going to need to go backwards and express it in like a spherical form or a cylindrical form. This is going to be a fine way to express it. So again, adding those two vectors together by first putting them into their component form, then we can easily add their like components, the i's, the j's, and the k's. In this case, there's 2 vectors we had to add together, and then we could get our resultant vector of 460i minus 40j minus 1080k newtons.